Welcome. Thank you all for coming here. I'm really excited to tell you about the research I've been doing for the past year and take you on a journey through robots. So my work is about using mobile robots for search and rescue and how we build environmental representations to support situational awareness for rescue. So if we want to do search and rescue and we don't have enough people, this is what we had to do for the past 50,000 years. Train a dog, and then your dog can help you finding people. And dogs are really great. They're autonomous, can smell really well, they have great scent, and they can work well on the team. Our problem is that these search and rescue missions can be very dangerous. So we're putting our four-legged friends in a lot of danger, and that's not a good thing. So that's why we want to introduce Spot. Spot is a robot dog, and the main benefit of that is that he's not alive, which means he cannot die. So we don't have to be sad if something bad happens. So that's what we're working on at trying to get Spot to help with these search and rescue tasks. So search and rescue, why should we care about search and rescue? Search and rescue is a very interesting group. Firstly, it's actually very relevant because with climate change and all the geopolitical turmoil, fortunately disasters are on the rise. Certain parts of Europe are already in trouble. There's not enough people to help here. So that's why search and rescue is very important. Then search and rescue take place in disaster scenarios. And disaster scenarios are very interesting from a decision-making perspective because they're actually very difficult. Time is very critical because lives are at stake. And we have incomplete information about our environment. And we have to make decisions based on tasks that we may not have discovered in the environment yet. They're not coming uphill. Solutions have been very large, potentially very large. So what do these search and rescue workers then need to do their work more effectively? They need situational awareness. And this is exactly where robots can help. The robots can help discovering tasks in the environment. And then rescue workers can make better decisions about how they are going to prioritize what they will be doing. So that's the goal, to create situational awareness, which will support the decision-making of these rescuers. And ideally also the decision-making of the robot itself. So a quick overview of what we'll discuss today. First, I'll go through my research questions. After that, we will discuss robot environmental representations, the background of that, how it's been done historically, what is the current state of the art there. Then we will look at behavior-oriented situational graphs, which is my proposed approach to representing the environment. And then we'll support that with some results. First the simulation, and then the real world, which will bring us to our conclusion. So let's start with the research question. How can we combine prior knowledge and perception of situations to construct and exploit more actionable environment representations for mobile robot missions? So pretty big sentence, let's decompose it a bit. So prior knowledge, what is that? Prior knowledge are all the assumptions that we can make before the mission starts. All the prior knowledge that we can put in the system, that we can use to help. Humans have a lot of prior knowledge, that's why they're so good at things. Robots, less so. Then the other part is perception of situations. So perception has been the largest enabler, one of the largest enablers in mobile robotics in the past 10 years. You can now perceive objects, classify them, and we are moving towards detecting situations. And then the goal of this thesis is to construct an actionable environment. Actionable, because we want to combine this prior knowledge and this perception into this actionable environment representation. And then finally, we also want to consider how we want to exploit that representation. Because that's very important. Now we construct it, is how we want to use it. So first we want to use it for situational awareness. And secondly, we want to use it to plan with the robot. The robot should be able to make plans from tasks using this environment representation. So those are the research topics that we'll cover. So primarily environmental representation and how should we structure this prior knowledge. Of secondary importance is the task planning. That's the reference implementation, and this perception is not the focus of this thesis. There we make very strong assumptions. But we are interested in how this all comes together. So the problem scenario, search and rescue. As I said, we have a large operational area, and we have this partly observable environment, so we cannot see the whole environment at once. We are moving with a global perception through the environment. This information needs to be aggregated. Our objectives are known, so we know that we have to go and assess victims to obtain information about victims. We don't know where the victims are or how many victims there are. So the tasks are added, specific tasks. So that brings us to the goals. My research is how do we construct this action representation of the environment? We want to include discovered tasks. We want it to be scalable, we want it to be plannable, and we want it to be. So before I tell you my approach, let's look at the state-of-the-art background. Let's start all the way at the start. So this is what we've been doing in the 60s. We want to navigate from A to B, and you can see the nice obstacle course here. So there are tons of obstacles, and we want our robot to navigate this environment without colliding with the obstacles. But that's the common approach that is to build a cell map. So we divvy up the free space into cells. For each cell we say is 3 years occupied. And using that we can navigate. These cell maps are pretty good. We can also scale them to 3D. And we have voxels. They're really good for this fine-grained work. So, however, only locally because they don't scale to large environments, especially not in 3D. So now let's take a very large look into the future. This is what we're able to do in lab settings. In very controlled simulation settings, we're able to extract these data-driven hierarchical 3D scene grabs environments, which is a lot to take in, but really what we've done here is we've aggregated all this. So I'll walk you through it from the bottom to the top. So the first layer, we just have our perceptions. See pieces of the couch, pieces of people, and then in the level above them, we can combine these pieces to find objects, such as the whole couch, the whole person. Then these objects are connected to places in level 3, so it's in front of the couch, next to the couch, and whatever. And these places we can cluster them to the playing rooms. And these rooms then together from the building. So here you see that there's a long corridor that connects several rooms, and in these rooms are all these objects. So this is a really comprehensive representation that has a lot of benefit. It's very scalable. It has this unified representation that's really nice. And we can do navigation in different directions. However, it also has several shortcomings. Because tasks are not represented explicitly, so it's still unclear what we should do with the representation. And also all the current state-of-the-art work focuses on constructing a scene graph and then planning of it. So there's nothing that generates and plans these together online. And also the relations are primarily switched. So I think it could be different. And that's why I designed research this behavior-oriented situation. So if we repeat the problem scenario, our goal is to construct this environment representation that meets these criteria. We make the assumption that we focus on go from A to B and do C-type task domains, plan domains, which is a very common plan domain. Because in search and rescue, generally we have to collect information. That's really what robots are good at now, going to places and collecting information. So first, let's focus on including these discovered tasks, because in the 3D spatial scene graph, we didn't see tasks. So how can we include tasks in our graph? So let's start with the basic navigation. So the graph G is comprised of nodes V and edges V. The nodes are circles and the edges are the lines between circles. So these nodes can correspond to waypoints, places the robot can go, and roll objects, these detected classes. And then the edges correspond to the robot being able to traverse it or look at it. So this still doesn't contain actions. Now we can go to places, and that's fine, that's nice. But what we want to do is we want to include tasks in there. So we want to assign meaning to these edges. And in order to do that, we associate these edges with behaviors. And if we successfully execute such a behavior, we assume that that will complete certain tasks. So now that we have this representation, this behavior-oriented graph, we can just add a node. It becomes very explicit that the agent counts 2 objects can perform for behaviors. You go to waypoint 3, you go to waypoint 1. And now task planning becomes possible because we can now find a sequence of these behaviors that will allow us to perform this assess behavior, which will result in accomplishing the stats. So now you might be asking, how do we know how to add these edges? How do we have the information of what behavior can we do where? That's where we introduce the new perspective of situational affordance. So given a situation that we've detected, we want to add a new node to the graph that's comprises with the situation. So we add a node, we want the agent is at some waypoint, detect this node. And now we want to add an edge to connect this node to our graph. And we do that using this situational affordance scheme. So our prior knowledge is structured in the situational affordance, and it connects situations with behaviors, mission objective. So using the affordance, we can see that for an unknown victim, the behavior would be to assess it. And we can add this edge between the waypoint the agent is at and the detected situation. And finally, we can also add an edge using the successful victims projected in the affordance, and that contains the reward for this task. Now, this is for a specific victim assessment, but the idea is this generalizes to any situation, behavior, mission objective pair. And this is a way to structure prior knowledge that allows you to perform these missions autonomously and discover these tasks. So now we've talked about how we can include discovered tasks. The next thing I want to talk about is how we can plan on this graph, because our graph is directly planned. So if we want to do planning on it, we define a planning problem P as a set, a graph G, a task tau, and an agent A. And then the resulting plan to accomplish that task by that agent would be the plan phi. So phi is defined as a sequence of edges over this graph. So how do we obtain this plan? Well, the great thing is that because we've constructed our graph like this, we can now use any generic graph searcher to find a path over the graph that corresponds to the sequence of agents. So using at and fact, we find a path from the node the agent is at, AV, to the node of the task edge, the target. Now, maybe there might be this path is then selected based on the lowest cost. So there might be multiple ways to get to our task. We choose the one with the lowest cost. That's what the graph shows. But there might be multiple tasks available, and then we can also compare ourselves using utility. We can divide reward over the cost and consider that trade-off for selecting what is the most optimal task. All right, so now I'll explain to you how the system works. Let's have a look at some results in the simulation. So this is the schematic view of the graph that I showed before. On the left is the view of the simulation. And you can see that this edge corresponds to that edge. It's just to give you an introduction to the simulation. So we see there's two unknown victims. The agent is at start, and it now has to select the task and go and perform it. So the agent selects to assess the first victim, and it will navigate there. From the assessment, it has discovered that the victim is immobile. Now that task is completed and moves on to the next task. And it assesses the second victim, and it has discovered that it's mobile. Right, so that's the simulation. This was basically a deploy problem. We saw that the environment was completely known to the agent beforehand. It knew the graph. They just had to select the task. Now with the real robot, we changed the scenario a little bit. We extended it. So we have, this is a 3D model of the real area where we ran the experiment. So it's 30 by 30 meters. And it's completely unseen for the robot. So it doesn't know the victim locations, it doesn't know the map. But there are 4 victims present. These victims are represented with QR code, like these. It's perfect for the perception system. So in order to explore this environment, we have to introduce some exploration. And that's what you see here. This is the first step of the exploration, the mission. But the agent has sampled frontiers. Frontiers are the green nodes around it. And what you can see is that the agent has actually a very limited perception range. So the grid represents the perception range of the agent, and it's only 2 by 2. So in that range, it can sample new. Now, if we sample these frontiers, then we go visit these frontiers and continue sampling, we can start to do our exploration. And here you see this step. And also some red nodes have been introduced, so waypoints, the places the agent has been. Now we continue our exploration. So first we discover this unknown victim. Then we continue exploration. Here we're about to make a loop closure. So we see that we're about to return to the place that we've been before. And we're able to connect the dots in our map. Here we explore the hallway in the back. And we find a second victim. Here we explore the narrow tunnel, and we have found the third victim. Finally, the exploration is complete. And we've found all 4 victims in the environment. And this is a recap. So that's the 3D model, and this is the graph we found. But we didn't use the 3D model in any way to obtain this graph. All right, that brings us to the conclusion of my presentation. So we've defined the behavior-oriented situational graph. We've demonstrated it in the search and rescue mission. We've shown that the representation is plannable and it includes behaviors. Finally, the representation has been shown to be deployed in simulation and in the real robot. That brings us to actually the most interesting part for me, the future work. This is what I can continue to work on at DNO. So the first thing would be to integrate with a real perception system to move to the assumption of the QR codes. And then we can start to run experiments with real people. The second thing that's my personal favorite would be to expand it with multi-agent planning. So we have multiple pods. How can we get these pods to cooperate in a non-naive way? So we have to allocate these tasks optimally between these agents. And finally, we should implement a more sophisticated exploration. Because currently the center range is very limited. If we had a larger center range, we could make our exploration way more guided and more thorough. That would result in much quicker exploration, much more effective. All right. Thank you all for coming here today. And that was it for my side. If you have any questions, I'm happy there. The audience.